Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we will explore the fundamentals of databases, what they are, why they matter, and how they help us manage and make sense of data. We'll look at different types of databases, understand how they store and retrieve information, and set the stage for deeper dives into relational, non-relational, and purpose-built database systems. Whether you're just getting started or brushing up your knowledge, this is your first step into the world of databases. Let's get started. Data forms the backbone of all digital systems. It represents raw facts, numbers, or symbols that, when processed, unlock meaningful insights. Let's break this down. Data comes in three primary forms: structured, semi-structured, and unstructured. Structured data follows strict formats like tables in a relational database. Think of neatly organized spreadsheets. Semi-structured data, such as JSON or XML files, has some organization but doesn't rely on rigid rules. Finally, unstructured data, like images, videos, or free text, lacks a predefined format but powers cutting-edge fields like AI and analytics. Where does data come from? Everywhere. User interactions, IoT devices, business transactions, system logs, and external APIs all generate data. This data can be quantitative, such as numerical sales figures, or qualitative, like descriptive customer feedback. Regardless of its type, data follows a life cycle: creation, storage, processing, analysis, and finally, archival or deletion. Data fuels decision-making, automation, artificial intelligence, and business intelligence. Organizations use data to streamline operations, enhance customer experiences, and outperform competitors. But managing data isn't simple. Challenges like scalability, security, governance, and compliance demand careful attention. This is where databases shine. Whether traditional relational systems or modern cloud-based solutions, databases store and manage data efficiently. They ensure structured storage, rapid retrieval, and reliable access, cornerstones for business and analytical applications. Structured data is the backbone of organized digital information. It follows a strict, predefined schema, ensuring it's easy to store, manage, and retrieve. Think of it as neatly arranged tables in relational databases like MySQL, PostgreSQL, SQL Server, or Oracle. Each piece of data fits into rows and columns, maintaining consistency and reliability. What makes structured data unique? First, its rigid schema. Before any data is stored, its format, data types, and relationships are clearly defined. This discipline ensures accuracy and order. Second, it's powered by SQL, structured query language, which allows precise filtering, sorting, and analysis. Need to find a specific customer record or analyze sales trends? SQL makes it fast and efficient. Real-world examples of structured data include customer profiles, financial transactions, employee databases, and inventory systems. Industries like banking, healthcare, and e-commerce rely on it because it adheres to ACID properties: atomicity, consistency, isolation, and durability. These principles guarantee data integrity, preventing errors or corruption even during complex operations. Traditionally, relational databases scaled vertically by upgrading hardware. But today, cloud solutions also enable horizontal scaling through read replicas and multi-region deployments, letting businesses handle massive data sets without sacrificing speed or availability. Structured data combines order, precision, and adaptability, a cornerstone for mission-critical systems in our data-driven world. Semi-structured data bridges the gap between rigid order and total chaos. Unlike structured data's strict tables, it uses tags, markers, or hierarchies to organize information. Think of it as a flexible filing system. There's no predefined schema, so it adapts effortlessly to evolving datasets, making it perfect for dynamic environments. Common formats like JSON, XML, YAML, Avro, and Parquet dominate web APIs, configuration files, and data exchanges. Instead of traditional relational databases, semi-structured data thrives in NoSQL systems where tools like JSON Path or XPath help query nested or hierarchical data with ease. Imagine log files tracking server activity, emails with metadata headers, or social media posts bursting with hashtags and geotags. These are all semi-structured. Its flexibility shines in large-scale applications. NoSQL databases scale horizontally, spreading workloads across servers to handle massive growth without breaking a sweat. This data type fuels big data analytics, machine learning pipelines, and real-time applications. Data lakes, for instance, rely on its ability to absorb diverse formats, from sensor readings to tweets, without upfront restructuring. But flexibility comes with trade-offs. Parsing and indexing semi-structured data requires advanced techniques to speed up retrieval, adding complexity. Semi-structured data is the Swiss Army knife of modern systems, versatile, scalable, and indispensable for innovation, even if it demands a bit more finesse to wield effectively. Unstructured data is a type of data that does not follow a predefined format or organizational structure, making it more complex to store, process, and analyze compared to structured or semi-structured data. Unlike structured data, which is neatly organized in tables, or semi-structured data, which has some level of organization, unstructured data lacks a predefined schema, giving it flexibility but making management more challenging. This type of data is often stored in data lakes, object storage systems and distributed file systems. Since unstructured data comes in a variety of formats, including text files, PDFs, images, videos, audio files, and sensor data, traditional relational databases are not well suited to store and process it. Instead, specialized tools are required to index, search, and extract meaningful insights. Unstructured data is everywhere in modern digital ecosystems. It includes social media posts, emails, customer reviews, IoT sensor data, medical images, and video recordings, all of which are continuously generated at an immense scale. The importance of unstructured data is growing rapidly, particularly in fields such as artificial intelligence, AI, machine learning, sentiment analysis, natural language processing, NLP, image recognition, and real-time media streaming. However, working with unstructured data comes with its own set of challenges, including high storage costs, complex data retrieval, security risks, and the need for advanced analytics tools to unlock valuable insights. Despite these challenges, businesses and researchers continue to leverage unstructured data to gain deeper insights and drive innovation across various industries. This illustration depicts the transformation of raw information into usable insights by showing how student data at XYZ University evolves from unstructured text to semi-structured JSON and finally into a structured tabular format. At the initial stage, data exists in a free-form, narrative format, typically as plain text found in documents, emails, reports, or conversations. In this case, the information about XYZ University and its students is presented in a paragraph that mimics natural human language. While it may be easy for a person to read and understand, it lacks any predefined structure or consistent format that a machine can readily interpret. For example, identifying student details such as names, IDs, courses, or specializations requires complex natural language processing (NLP) techniques because the data is mixed with descriptive phrases and sentence-level context. There are no clear delimiters or labels indicating which pieces of information correspond to specific attributes. This makes unstructured data difficult to search, sort, analyze, or integrate with other systems. Despite containing valuable insights, it is not immediately actionable without further processing. Extracting structured meaning from this type of data typically involves parsing, tagging, and transforming it into more organized formats, setting the stage for downstream use in applications and analytics. In the next stage, the information is transformed into a semi-structured format, commonly represented using standards like JavaScript Object Notation, or JSON. Unlike the unstructured narrative form, semi-structured data organizes the content into key-value pairs, where each piece of information is labeled and grouped logically. For instance, details about each student such as their ID, name, course, and specialization are enclosed within a structured block under a student's array. This format doesn't enforce a rigid schema like relational databases do, meaning different records can have different fields, e.g., a student may or may not have a specialization listed. However, it still introduces enough structure to allow programs to interpret, extract, and manipulate the data efficiently. This semi-structured format acts as a bridge between free-form, unstructured text and the highly organized world of structured data. It makes the data machine-readable, searchable, and easier to process programmatically, paving the way for automation, integration with APIs, and eventual transformation into fully structured databases. In the final stage of data refinement, information is structured using the relational database model. Data is normalized and distributed across multiple interlinked tables, each representing a specific entity, such as student, course, and specialization. Unique identifiers like student ID, course ID, and specialization ID serve as primary keys, ensuring data integrity. Relationships between tables are established through foreign keys, enabling efficient cross-referencing and enforcing referential consistency. For instance, the student table uses course ID and specialization ID to point to relevant entries in the course and specialization tables. This structured relational form enables powerful querying, streamlined updates, and scalable data management for complex, interrelated data sets. Structured data is highly optimized for indexing, which speeds up data access. One can use standard query languages like SQL to retrieve, filter, and join data across multiple tables. This structured representation marks the completion of the data refinement journey. It turns raw, narrative information into a format that is both machine-friendly and business-ready, enabling scalable, repeatable, and real-time decision-making processes. This flow from unstructured text to semi-structured formats to structured data highlights how raw information is processed and refined into a usable form. It's a critical part of data management in organizations, enabling insights and decision-making through clean, organized, and accessible data. Databases come in various types, each designed to handle specific data storage and retrieval needs. Relational databases, RDBMS, are among the most common, organizing data into tables with rows and columns following a predefined schema. These databases use structured query language for querying and enforcing data integrity through ACID, atomicity, consistency, isolation, durability properties, and are widely used for transaction-based applications. On the other hand, NoSQL databases offer a flexible alternative to relational databases, designed to handle unstructured and semi-structured data with ease. They don't rely on a fixed schema and are built to scale horizontally, making them ideal for high-velocity data and large datasets. NoSQL databases can be further categorized into different types, such as document stores, which store data in flexible document formats like JSON, and key value stores, which store data as pairs of keys and values. Another category includes column family stores, where data is organized into columns instead of rows, offering efficient storage for large volumes of data. Lastly, graph databases are designed to manage data relationships, representing them as nodes and edges, making them ideal for network-driven applications. Object-oriented databases are designed to store data in the form of objects, similar to how data is represented in object-oriented programming languages. These databases are particularly useful when dealing with complex relationships between objects, allowing developers to preserve the structure and relationships of data in a more natural way. Purpose-built databases are essential for meeting the unique demands of specific applications and workloads. These databases are optimized to handle particular types of data, offering superior performance compared to general-purpose databases. For example, time series databases are designed specifically to handle time-stamped data, such as sensor readings or logs, enabling faster and more efficient storage and retrieval of such data. One of the key advantages of purpose-built databases is their ability to offer scalability and flexibility. As business needs evolve, these databases can scale horizontally, making them ideal for handling large volumes of data. NoSQL databases, for instance, are well suited for managing unstructured or semi-structured data, providing flexibility in terms of schema and data models while also enabling growth. Data modeling is another area where purpose-built databases shine. For example, graph databases are specifically designed to store and query relationships between data points, making them particularly useful for applications like social networks, recommendation engines, and fraud detection. This tailored functionality allows these databases to solve complex problems that general-purpose databases might struggle with. These databases also provide better availability and fault tolerance. Many purpose-built databases are designed with high availability in mind, ensuring that even in the event of failures, the system can continue to operate. This is particularly important for mission-critical applications where downtime can have significant consequences. Purpose-built databases help speed up development processes as they provide the right tools and features for the task at hand. For instance, using a document database allows developers to store complex, hierarchical data structures easily without having to define rigid schemas, which accelerates development cycles. Overall, purpose-built databases enable organizations to achieve better performance, cost savings, and scalability, while simplifying development processes and ensuring that applications meet their specific data management requirements. A relational database management system, RDBMS, is a structured approach to storing and managing data, organizing information into well-defined tables with rows and columns. This structured format ensures data consistency and integrity, making RDBMS an ideal choice for applications that require a clear schema and reliable transactions. One of the key strengths of RDBMS is its adherence to ACID, atomicity, consistency, isolation, durability properties, which guarantee that transactions are processed reliably, even in cases of system failures. This makes it highly suitable for applications where data accuracy and consistency are critical, such as banking, e-commerce, and enterprise resource planning (ERP) systems. RDBMS relies on structured query language (SQL) for querying and managing data, allowing users to perform complex operations, including joins, aggregations, and nested queries. This capability is particularly useful when dealing with data relationships, as relational databases enforce primary and foreign key constraints to maintain structured associations between tables. With their structured approach, transaction reliability, and security features, relational databases continue to be a cornerstone for enterprise applications. Popular RDBMS solutions include MySQL, PostgreSQL, Oracle Database, Microsoft SQL Server, and IBM DB2, each offering powerful capabilities tailored to various business needs. In the world of relational databases, data isn't just thrown into a system. It's carefully structured, organized, and maintained for efficiency, integrity, and performance. At the heart of this system lies the table, the fundamental building block of any relational database management system, RDBMS. Think of each table as a digital version of a spreadsheet, where rows represent individual records and columns define the attributes of the entity the table represents. For example, a student's table might include columns like student ID, name, major, and enrollment date. To ensure each record is uniquely identifiable, primary keys come into play. A primary key is a special column or combination of columns that guarantees every row is distinct, like a student's ID number that no two students share. But the real power of relational databases emerges through foreign keys, fields in one table that reference primary keys in another. This is how relationships are formed. A course enrollments table might use a student's ID as a foreign key to link back to the students table, weaving a rich web of interconnected data. As databases grow, retrieving data quickly becomes a challenge. This is where indexes prove invaluable. Much like an index in a book, database indexes allow systems to locate data without scanning every row, dramatically speeding up queries, especially on massive datasets. To keep the data clean and consistent, databases apply constraints. These rules act like gatekeepers, preventing errors and enforcing logic. For instance, a not null constraint ensures that a column cannot be left empty, while a unique constraint prevents duplicate values. Combined with check, default, and the key constraints, they safeguard the integrity of the information. All of these elements, tables, keys, constraints, and indexes, are organized within a schema. A schema defines the logical structure of the database, dictating how data is arranged and how its components relate. It provides a blueprint that brings order to complexity, ensuring that everything from data types to relationships is consistently maintained. Beyond storing data, databases also carry out operations using stored procedures and functions. These are blocks of reusable SQL code that encapsulate logic, calculations, and repetitive tasks. They not only streamline workflows but also boost performance by executing operations directly within the database engine. Finally, triggers add a layer of automation. These are scripts that run automatically in response to certain events, like when a record is inserted, updated, or deleted. Triggers enforce business rules, maintain audit trails, and ensure that changes ripple through the database in a controlled and consistent manner. ACID compliance is a fundamental principle in relational databases, ensuring that transactions are processed reliably and maintain data integrity. It consists of four key properties: atomicity, consistency, isolation, and durability, each playing a crucial role in preserving the accuracy and reliability of data. Atomicity guarantees that a transaction is treated as a single indivisible unit. If any part of the transaction fails, the entire operation is rolled back, preventing partial updates that could lead to inconsistent data. This ensures that either all changes are successfully applied or none at all. Consistency enforces that the database remains in a valid state before and after a transaction. Transactions must adhere to all integrity constraints and business rules, preventing corruption or invalid data from entering the system. This safeguards the accuracy of critical information, such as financial records or inventory levels. Isolation ensures that concurrent transactions do not interfere with one another. In multi-user environments, different transactions might be executed simultaneously, leading to potential conflicts. Isolation levels control how transactions interact, preventing issues like dirty reads, non-repeatable reads, and phantom reads, thus maintaining data accuracy. Durability ensures that once a transaction is committed, its changes are permanently recorded, even in the event of a system crash or power failure. By storing data in non-volatile storage, databases guarantee that committed transactions are never lost, making them reliable for mission-critical applications. Beyond these core principles, ACID compliance also helps in preventing data corruption, enforcing concurrency control, and providing robust rollback and recovery mechanisms. If a transaction encounters an error or failure, the database can revert to its previous stable state, ensuring that incomplete or erroneous operations do not impact data integrity. ACID compliance is essential for mission-critical systems such as banking, e-commerce, healthcare, and enterprise applications, where even minor inconsistencies can have significant consequences. By adhering to ACID principles, databases provide a strong foundation for secure, reliable, and accurate data management. Non-relational databases NoSQL offer a flexible and scalable alternative to traditional relational databases, making them well-suited for modern applications that require high performance and dynamic data structures. Unlike relational databases, which enforce a strict schema, NoSQL databases support a flexible schema, allowing data models to evolve over time. This adaptability is particularly useful for applications dealing with semi-structured or unstructured data, such as JSON, XML, multimedia, and social media content. One of the key advantages of NoSQL databases is their scalability. Unlike relational databases that primarily scale vertically by adding more computing power to a single server, NoSQL databases are designed for horizontal scaling, enabling data distribution across multiple servers. This makes them ideal for large-scale, high-traffic applications where handling massive amounts of data efficiently is crucial. NoSQL databases support a variety of data models, each optimized for different workloads. Document stores like MongoDB are excellent for applications requiring flexible data structures. Key value stores like Redis offer ultra-fast performance for caching and session management. Column family stores like Cassandra are built for high-speed analytical processing, while graph databases like Neo4j efficiently manage complex relationships in social networks and recommendation engines. In terms of performance, NoSQL databases excel in handling high-throughput, low-latency operations, making them ideal for real-time applications such as e-commerce, IoT, recommendation systems, and real-time analytics. They achieve this by prioritizing eventual consistency over strict ACID compliance, ensuring better availability and partition tolerance in distributed environments. Because of their ability to handle big data and accommodate a variety of data structures, NoSQL databases have become the preferred choice for social media platforms, content management systems, and cloud-native applications. Their optimized designs for specific workloads enable businesses to achieve higher efficiency and scalability, making them an essential component of modern data architectures. Base compliance is a fundamental principle followed by many NoSQL databases, offering a more flexible and scalable approach to data management in distributed environments. Unlike ACID-compliant databases, which prioritize strict consistency, Database systems focus on availability and fault tolerance, making them ideal for high performance applications that handle massive amounts of data. The basically available property ensures that the system always responds to requests, even if the data is not immediately up to date. This means that users can access the database without delays, but the information retrieved may not always reflect the latest updates. The concept of soft state further supports this by allowing the system to change over time, even without direct input, as data is asynchronously replicated across multiple nodes. A key characteristic of base compliance is eventual consistency, meaning that while data updates are not immediately synchronized across all nodes, they will eventually converge to a consistent state over time. This trade-off enables NoSQL databases to achieve high availability, ensuring that services remain operational even in cases of network failures or distributed system disruptions. Base-compliant databases are designed with partition tolerance, meaning they can continue functioning despite network partitions, making them highly resilient and fault-tolerant. Additionally, they are optimized for horizontal scaling, efficiently distributing data across multiple servers to accommodate increasing workloads. Many modern NoSQL databases, such as Cassandra, DynamoDB, and CouchDB, embrace base principles, favoring performance and availability over strict consistency. This makes them particularly well suited for applications like social media platforms, real-time analytics, online gaming, and large-scale web applications, where rapid access to data is more critical than immediate consistency. By sacrificing strong consistency for better availability and scalability, base compliance provides a robust alternative to traditional relational databases, enabling businesses to build highly distributed, fast, and resilient applications in today's data-driven world. AWS offers a broad spectrum of purpose-built database services, categorized by data models and optimized for specific application needs. This allows developers to select the most appropriate tool for the job rather than relying on a one-size-fits-all approach. Relational databases like Amazon RDS, Aurora, and Redshift are ideal for structured data and use cases requiring complex querying, transactions, and strong consistency. Key-value stores such as DynamoDB and Keyspaces offer fast, scalable access to simple data structures, making them well-suited for high-performance, low-latency workloads. In-memory databases like Elasticache and MemoryDB are designed for microsecond read-write access, commonly used in caching and real-time applications. Document databases such as DocumentDB support flexible, semi-structured data models like JSON, perfect for applications that require a dynamic schema. Graph databases, exemplified by Neptune, help uncover relationships and connections across data, ideal for social networks, recommendation engines, and fraud detection. Time series databases like TimeStream are purpose-built to efficiently handle timestamped data from IoT devices, logs, or monitoring systems. Ledger databases, such as Quantum Ledger Database (QLDB), provide immutable, cryptographically verifiable records for use cases like audit trails and financial systems. Finally, the Amazon Data Migration Service (DMS) supports seamless data transfer across these diverse systems, simplifying cloud adoption and modernization. With a wide range of database options available, selecting the right one is critical to application performance, scalability, and cost efficiency. AWS offers purpose-built databases optimized for specific data models and access patterns. Understand data structure. The first step in choosing the right database is understanding the structure of your data. If your data is highly structured, relational databases may be ideal. If it's unstructured or semi-structured, you might consider NoSQL options like document, key value, or graph databases. Performance and speed. Consider the performance requirements of your application. In-memory databases are suited for real-time applications where low latency is critical, while time series databases excel at handling large volumes of timestamped data with fast read and write operations. Scalability needs. Think about your application's growth over time. NoSQL databases offer horizontal scalability, making them a good choice for applications that need to handle large volumes of data or scale quickly. In contrast, relational databases often scale vertically and may be more suitable for applications with more static data requirements. Consistency and availability. Determine the level of consistency and availability required by your application. If ACID compliance, atomicity, consistency, isolation, durability is essential, a relational database or NoSQL database might be the right choice. If the application can tolerate some inconsistency for the sake of availability, a NoSQL database with eventual consistency might be more appropriate. Data relationships. Consider the complexity of the relationships between your data. If your data model involves complex interrelated data, graph databases are ideal for representing and querying such relationships. For simpler, tabular data, a relational database may suffice. Querying requirements. Think about the types of queries you need to perform. If your queries are complex and involve join operations, a relational database may be the best choice. However, if your queries are more flexible and involve large amounts of unstructured data, NoSQL databases like document stores might be more suitable. Security and compliance. Make sure the database you choose meets your security and compliance needs. For industries with strict regulations, ensure the database supports the necessary encryption, authentication, and auditing features required to meet legal and regulatory standards. Cost and maintenance. Consider the total cost of ownership, including both infrastructure and ongoing maintenance. Cloud-based databases offer managed services that reduce the operational overhead, while self-hosted databases might give you more control but require more effort in terms of updates, backups, and scaling. By aligning your workload characteristics with the strengths of each database type, you can maximize performance, reduce operational complexity, and build more resilient and scalable applications. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.